Okay.
Okay. So now we're going to talk about the ionosphere, which is how we actually propagate signals much farther than line of sight. It can actually go completely around the world back to yourself and hear an echo in some cases. So the ionosphere is really sections of the atmosphere that get charged up or ionized by radiation from the sun.
Mm-hmm.
And those ions can actually diffract or refract radio waves.
Basically pushing it back down. Is that like basically pushing it back down towards the Earth?
Well, it bends it.
Bends it back? Yeah, okay.
It can. It depends on the angle and the frequency,
okay,
amongst other things.
Mm-hmm.
Now you can look at the picture and see the sun, and then the shadow, nighttime over here. So you can see that the four layers that you have in the daytime, it starts with the D, the E, and the F layer, which is split into F1 and F2, kind of collapse at night. So we basically have an F layer that's combined into a single layer, and a very weak E layer, and no D layer at night, which is why communications are different between daytime and nighttime. If you remember, like AM radio at night, you might be hearing stations, many states away, but not in the daytime.
No, yeah.
Because those low frequencies where AM radio is and the lower part of the amateur radio band get absorbed by the D layer at night. I mean, in the daytime. And
it's a
the D layer
band,
disappears, so it doesn't absorb it. So you can use those frequencies much better at night. The ionization of the ionosphere is totally dependent upon solar activity, particularly sunspots.
Yeah.
The more sunspots, the more ultraviolet and X-rays that you have coming out to ionize the ionosphere. So the outer layer, like F2, is receiving the highest radiation, but the atoms and molecules are very far apart. It's very sparse. So some of the radiation manages to keep penetrating to get all the way down to the D layer in the daytime. So you kind of have that absorption of the ionizing radiation through the different layers. So you don't get as much of it down to the D layer as you do out in the F layer. So you get much more refraction on those outer layers. And that's how we get the most distance, because they're the highest, which should have another chart shortly showing that. So we talked about VHF. It was mostly line of sight, and they don't get refracted by the DE and F layers. They tend to go straight through, which is how we can talk to satellites on VHF and UHF. there is the possibility of some bounce off of the E layer. It's very sporadic, and we call it sporadic E. It's not very dependable for communications. And it works best on the 10, 6, and 2 meter frequency bands. And the 10 meter band, which as a technician, you'll be able to operate on voice in that small section, works the best during the day between sunrise and sunset, depending on the sunspot activity. The more sunspot activity, the better the 10 meter band is. Huh. It's been off and on very good here the last year. And we'll talk about the cycle, the sunspot cycle with the sun is an 11-year period.
Oh,
and we passed the peak about a year ago. So we're actually going downhill, and it'll be 9, 10 years before we get another peak. So in the valley, radio communications is not going to be very good. And I don't know why the sun is 11 years, but it is. And I think we're on since they started counting them, I think we're on the 25th cycle. This is showing the relative layers. You see the D layer in brown, the E in green, and the F layer up here in blue. What the height is approximately for those, and what kind of hop you can get. If you notice the red line being refracted up in the F layer, it's going out maybe 2,200, 2,400 miles.
Wow.
Whereas a signal that's being refracted like sporadic E off the E layer is maybe getting 1,200, 1,400. This is just showing that with increasing frequency, what happens. So low frequencies, like I said before, in the daytime are getting absorbed on the D layer. As we go up in frequency, we can get some refraction or diffraction off of the E layer. And then we go a little higher, we start getting some F1 refraction, a little higher and higher angle, and we're getting F2. So you can see each one of those is going farther. Mm-hmm. But at a certain point, we get to a frequency where it's going to go straight through. And that's typically when you're above 100 megahertz. So which of the following types of propagation is most commonly associated with occasional strong signals on the 10, 6, and 2 meter bands from beyond the radio horizon?
It would be Bravo. Sporadic E. Sporadic.
Very good. This is just showing what we call skywave propagation when we're actually refracting off of the F layer. And those angles are what we call takeoff angle, and we'll talk about that a little bit later. But the antenna pattern actually radiates in lobes, and depending on the elevation of that lobe determines where the maximum signal strength is, and that affects the height. It's just like reflecting a signal off of a piece of glass. Mm-hmm. When you're below the critical angle, it will reflect, And when you get above it, it goes straight through. Radio is kind of the same way. So it's the critical angle and the frequency that determines. If you look over on the left, it's kind of an exception where if you have an antenna that's very low to the ground, it tends to radiate almost vertically. And we call that NVIS, or near vertical incident something. I forgot what S is. Mm-hmm. Which actually allows us to communicate over short distances, where if we're doing the typical one, you're not going to contact anybody in this region here under the hop.
Right.
Military uses NVIS a lot.
Yeah, troposcatter communications. That's what we did. Our signal would go about 100 and maximum, I think it was like 125 miles. But normally the best range was what they have here, about 100, 105.
Yeah.
We were sweeping our antennas. We were sweeping, just making all those adjustments. We called it Mickey Mouse. We called it Mickey Mouse because we had two microwave antennas that would be popped up. So if you're looking at it in a distance and coming up a hillside or something, it looked like Mickey Mouse. Got the two ears, and then there's the van, the rig.
Yeah.
But that's what we did.
Okay. Some other propagation phenomena is auroral backscatter, where you actually kind of bounce the signal off of the northern or southern aurora.
Huh.
There's meteor scatter. As a meteor comes through the atmosphere, it's generating so much heat that it creates a plasma, and it leaves a trail of ionized atmosphere behind it, like a long cylinder.
Mm-hmm.
It's possible to bounce radio waves off of those meteor trails. It's only good for maybe 30 seconds to a couple minutes. So people do it. I've never seen it, but I guess you really have to know when the meteor's coming and a lot of things in order to do it. There's a thing called tropospheric scatter and also tropospheric ducting, which takes place when you have an inversion layer. We'll talk more about each of those.
Okay. So
auroral backscatter is bouncing the signal off the aurora. There's the aurora borealis, which is the northern one, and the aurora australis, which is the southern one. And they're both regions where the Earth's magnetic field and the interaction of the solar wind creates this ionizing effect. And actually, you see them illuminated. They call them the northern lights or the southern lights. There was a period, many months ago, I forgot exactly, where there was so much activity that people in Georgia could see the northern lights.
That would have been April.
That sounds about right.
Because we were in Scotland. We were supposed to be able to see it, except we had, of course, cloudy skies and rain, so we didn't get to see it. But we heard about it. There were a couple of events.
Yeah. Well, this coming thing might do it too.
Cool. You talk about the one in October?
Yeah.
Okay. They say it's supposed to be like a super storm. Really powerful.
A mass ejection?
Yeah. I think that's what he didn't say that. He just said it's going to be really, really big.
Yeah.
A lot of
actually, we've never had a direct hit from a coronal mass ejection I'm aware of. If we do, it will take out communications.
Well, that's what
It'll
this guy
affect the power grid. It'll be bad news.
Yeah. I don't know. I mean, this guy may be a doom and gloom thing. He says whatever it is, it's supposed to be really big October 30th.
Well,
For about,
because the sun's rotating, when
Mhm.
it gets ejected, you know, they usually miss us.
Yep. Thankfully.
But one time they're not.
Yeah.
One of the problems with the auroral backscatter is it's kind of like sporadic E. You get
Okay.
very distorted signals, varying strength. It's not a very reliable way to communicate. There's a picture
Oh,
from
cool.
2 years ago showing, I don't know how they generated it, but showing the north and south. And you can see in the daytime, in the nighttime, it's much more visible.
Hmm.
Um, it's interesting is the southern one is way off center.
Wow.
I have no idea why.
Hmm.
So, what is a characteristic of VHF signals received via auroral backscatter?
I would say bravo.
Okay. Okay, meteor scatter.
Hmm.
If you got meteor trails, they will refract or diffract radio signals.
Would that just be like during the times where we have the meteor showers? What is it? I think it's in the constellation of Libra. There's supposed to be a couple of them, a couple times a year that these showers occur. Is that
Yeah, well, that would
when people try this the most?
probably. I mean, that's where you're going to have most. I mean, you occasionally have a meteor, you know, all the time.
Right.
Um, but during these predicted showers, I mean, you have a better chance of getting one
I
because
know
you
they're
know when
called.
they're going to happen.
It's the Leonid showers. So I
Yeah,
think, huh,
that's one of them. Yeah,
that's yeah, there's a couple of them, but
it's
that's
something
one
I've never tried. I don't know if I want to go out in the middle of the night and do it.
Nah, I don't like the mosquito bites.
But it works the best on the 6 meter band.
Hmm.
Why I don't know. But 6 meter, I think, is better for sporadic E also. So, what band is best suited for communicating via meteor scatter?
Oh, that's a hard one. Bravo.
You were listening. Okay, tropospheric scatter is that the troposphere is the lowest region of the atmosphere, goes up about 6 to 10 kilometers. And some UHF and super HF frequencies sometimes are scattered as they go through the troposphere. And scattering kind of makes them go in all different directions, but I mean, some of them might be coming back down to Earth. So you
Right.
might be able to actually make a connection. Although it's going to be weak and it's not going to be necessarily stable. Kind of showing where the main signal is just kind of blasting right through, but you do get some scattering off of the particles and things in
Yeah,
that.
yeah, you hope for that bottom one.
Even the dust particles can cause some scattering.
Yeah.
And tropospheric ducting. If you have a temperature inversion where you wind up with a warm layer of air above a cooler layer, which isn't normally the case because normally as you go up in altitude, the air gets cooler and cooler. So an inversion is where you, as you go up, you run into a warmer air layer.
Sounds
And
like a
it kind
storm
of
to
creates a
me.
boundary, and it makes a tunnel.
Huh.
And a radio wave can bounce its way through that tunnel for long distances. They claim 300 miles or more.
You just have to have the right conditions for something like that, though, right? I mean, that's almost
Correct.
sounds like weather. It's weather related.
Right, it is. And I think it's more than likely going to happen over water.
Ah,
So maybe over the ocean, you might get farther.
I don't want to take that rig out there.
This is just showing, where some of the waves actually, refract in that sort of tunnel,
Mm-hmm.
and some of them make it on through. Now, it turns out when they refract off that boundary, they don't lose much energy. When they hit the earth and reflect back, they do tend to lose energy. So you can't just bounce forever, because every time it reflects or refracts off of something, you lose part of the energy.
Yeah. Well, we had ours. We had ours about like 100. Was it? Yeah. We wouldn't push it past 112 miles, but we had like a rig in Pensacola, Tallahassee, then Camp Landing, and then Orlando. Just
Okay.
try to go end to end just to prove that we could do it.
Yeah. So what type of propagation is responsible for allowing over-the-horizon VHF, UHF communications to ranges of approximately 300 miles on a regular basis?
On a regular basis?
Well, I guess you could do it regularly as long as the tunnel was there.
Yeah, the tunnel is there. Yeah, that would be the tropospheric ducting A alpha.
What causes tropospheric ducting?
The warm and the hot air. Warm updrafts from tornadoes and Delta.
Okay, we talked a little bit about precipitation. So basically, any form of water absorbs the higher frequencies and have virtually no effect on low frequencies down in the HF band. So we can transmit fine in a rainstorm, but if it's a lightning storm, you don't really want to do that. Antennas tend to be lightning attractors.
Mm-hmm.
And you don't even have to have a direct hit. I know some people who found out the hard way.
Mm-hmm.
This is just some graph I found. Kind of shows the amount of absorption. I think this little bump here has something to do with oxygen molecules. So at a certain frequency, they really absorb a lot. But you can see the absorption rate goes up as the frequency goes up. And I have no idea what the green line is. So what weather condition might decrease range at microwave frequencies?
I would have to say Charlie.
What's the effect of fog and rain on signals in the 10 and 6 meter bands?
I think I missed that one. Let's see. That would be sporadic.
Which
I don't
one?
know.
You don't know.
No.
Well,
I mean, it depends. Yeah. It's. I know it's going to. Oh, okay. I'd have to say alpha absorb, but I don't know for sure. That's it.
well, remember we
Oh
absorb.
no, that's right. Because 10. Wait a minute. 10 was.
Yeah, where is 10 and 6?
That's the ones that we can communicate. So. Okay, I'm gonna say delta. I don't know. Ah,
6
38.
meters,
Okay,
six
38.
meters,
Okay, I had the wrong numbers in my head. Okay.
6 meters is 50 megahertz. It's the low end of VHF.
Yeah.
Okay, so we talked sporadic E on the 10, 6, and 2, getting over the horizon. Auroral backscatter, meteor scatter on 6 meters. Might be interesting to try that in a real meteor storm. You never can tell. Tropospheric ducting. I'm not sure exactly where you go to find out where there's a duct.
In a storm front, I would say in a what do you call it? A weather front. That's the only place I can think of that actually happening.
Yeah, I could call the weather service in Melbourne and ask them where the nearest tropospheric duct is.
Because all that, when you look at that, that's like tornado conditions when you have the cool air getting trapped by the hot air. Isn't that right? Or is it the other way around?
Uh, I think there's an effect like that. I'm not sure.
I know it's one or the other, that you look for, and it's like tornadic activity, high pressure overtaking a low pressure so fast.
Yeah.
So maybe it's cold over high. I don't know.
And of course, precipitation, which absorbs the high frequencies, has very little effect at 6 meters.
Gotcha.
That's where it starts to have an effect. So they don't say no effect on 6 meters, they say little effect.